In this video, I want to take a look at another technique of using power series to find solutions to differential equations, in particular when you have initial conditions. I'm going to start by reminding you that the Taylor series of a function is this power series that involves the derivatives of the function at some x0. So f of x0, f prime of x0 times x minus x0, second derivative of x0 divided by 2 times x minus x0 squared, third derivative divided by 3 factorial x minus x0 cubed plus the fourth derivative at x0 divided by 4 factorial x minus x0 to the fourth, and so on, right? Here it is in summation form. And it is just a power series. It's just that the coefficients are being calculated in a very specific way. So I look at it and I say, well, the a sub n is the nth coefficient, and a sub n is going to be given by this calculation. What I'm going to do is I'm going to find all the derivatives, and so then I can divide by n factorial, and I can get my a sub n's and write down the power series. So here we go. I'll do it with an example. This is an example we did in the previous section, so we have some idea what the solution should look like. Y double prime minus x times y prime minus y equals 0. This time I'm going to give initial conditions of y of 0 equals 2 and y prime of 0 equals 3. Okay, so what I can do, well, first of all, notice that the 2 here is y0. Sorry, is a0. a0. It is also y0, but a0 because the 0th derivative is just the function, and so the function value here is 2, and you divide by 0 factorial, which is 1, so a0 is just that value of 2. Likewise, a1 is this 3, because a1 would be the first derivative at x0, that's what the 3 is. So 3 divided by 1 factorial, which is just 1. 3 divided by 1 factorial is 3, and so a sub n is 3. So this is a0 and this is a1. Okay. Now to find a2, I need to know the second derivative. But I've got an equation that tells me the second derivative. Right? Take this differential equation, move everything over to one side except for the second derivative there, and you can just say, hey, I know at x equals 0, I know the derivative, I know the function value, so I can plug those values in. So 0 is the x value, 3 is the derivative, 2 is the function value, and that calculates to be 2. So I know that at x equals 0, the second derivative is 2. And since I know the second derivative is 2, then I can calculate a2 by plugging it into that formula. 2 divided by 2 factorial is 1. So a2 is 1. Now, you might say, but how do you find the other derivatives? Well, I can find the third derivative by implicitly differentiating this equation right here, right? Because the derivative with respect to x on the left-hand side will be the third derivative. Derivative with respect to x on the right-hand side, well, there's a product rule, and then there's this. So the product rule would give me x times y double prime here, plus the derivative of x times y prime, which is here, and then the derivative of y is the derivative of y. These two combine to be the 2y prime. So the third derivative would be x y double prime plus 2y prime at x equals 0. I know y prime, that was given. I know y double prime because I just calculated it. So I can plug all that in. X is 0, y double prime was calculated up here as 2, plus 2 times the first derivative, but the first derivative was that initial condition there, 3. And I get that y triple prime is 6. Now I want to, y triple prime is 6, so a3 is 6 divided by 3 factorial, which happens to be 1. Okay. To get the fourth derivative, implicitly differentiate again. So on the left-hand side, I'm going to get the fourth derivative. Slide this up some. Derivative of that would be the fourth derivative, and then I'm going to do the derivative of this, which, again, there's a product rule, and derivative of that. So the product rule gives me x y triple prime plus the derivative of x times y double prime plus the derivative of 2y prime, which is 2y double prime, These two get together to get a 3y double prime, and then I'm going to plug in the information I know. I just calculated, oh sorry, x is 0. I calculated that y triple prime was 6, and y double prime we calculated earlier was 2. So there's the 6, there's the 2, and there's the x equals 0 plugged in, and again, and here I get that the fourth derivative at 0 is 6. And so a4 is 6 divided by 4 factorial, which happens to be 1/4. Okay. And you can see I could continue doing this over and over again. Just keep implicitly differentiating, plug in the information you know. Implicitly differentiate, plug in the information you know. Each time you get that next derivative, which then allows you to say that derivative divided by n factorial is the coefficient you need in your power series. So what we've done is we've calculated this power series here, at least the first 5 terms, 2 plus 3x plus x squared plus x cubed plus 1/4 x to the 4th, and I could continue on. Theoretically, once in a while, let's put it that way, I might recognize a pattern of what was going on here. I could recognize a pattern in these derivatives and predict what that next derivative would be. I think that's very rare, particularly in an introductory differential equations class. So we would just say, let's just do this out to 5 places or 7 terms or whatever it is, however many terms you think is going to be enough, and get an idea of how this is working. Okay. Now I want to double check because we did this in the previous section without having A0 and A1 known, and we got this as the solution. This is in the video of the previous section. And so just plugging things in here, now that I know that A0 is 2 and A1 is 3, every place I see an A0, I'm going to plug in a 2, and every place I see an A1, I'm going to plug in a 3. And sure enough, the 2 over 2, so this is 2 plus 3x, those match. The 2 over 2 is 1, the 3 over 3 is 1, the 2 over 8 is 1/4, and it would continue to work as well. Okay. What was easier, last time or this time? Okay. I'm thinking this one was a little easier. Although I also think that I'm more likely to see patterns the other way. Let's do the same one again, but this time let's let the initial conditions be at x equals 1. Right? It's the same differential equation, the same A0 and A1, but I'm doing it now at x equals 1. Graphically, right, the initial conditions are saying, the first initial condition is saying I want it to go through this point, and then the second initial condition is saying I want it to have this slope as it passes through that point. So what I'm doing here is I'm saying, rather than starting at 0 with a particular slope, you're saying move over to 1. So it just slides it over, but it's the same altitude, same height, same slope, just here versus there. And then there's a question of what does that do to the solution? Right? So with this now has x0 equals 1 rather than x0 equals 0. So my power series is going to sliding back up here. My power series is going to look more like this one because I'm going to have an x minus 1 as opposed to x minus 0s, which were just x's, right? So it'll look a little bit different there, but a lot of it is the same because I'm still doing the same thing. I'm going to take my x value, my y value, and my y prime value and plug it in, right, to find out y double prime. So there's x, there's y prime, and there's y. And this time y double prime is 5. So with y double prime of 1 equals 5, then the second coefficient, a2, is 5 divided by 2 factorial. Differentiating, this doesn't look any different than it did before. It's the same function, and the derivative is the same here. So the third derivative is x times y double prime plus 2y prime. And plugging in now, x is 1. The second derivative was just calculated as 5. And then 2 times the first derivative, which is the initial condition there, 3. And we get that y triple prime is now 11. Okay, so with y triple prime of 1 equal to 11, then a3 is 11 divided by 3 factorial. and so on. Take the next derivative. Again, this derivative looks exactly the same like it did above, but I'm going to plug different values of x in and y double prime in because, well, x is 1. The third derivative here is 11 plus 3 times the second derivative, which was 5. And so 11 plus 15 is 26. The fourth derivative is 26. And a4 is 26 divided by 4. And we could continue to do this if we wanted to get the fifth derivative, the sixth derivative, and so on. You just keep taking derivatives, plugging in the values, seeing what you get. And so the power series we get here is 2 plus 3 times x minus 1 plus 5 halves times x minus 1 squared plus 11 over 3 factorial x minus 1 cubed plus 26 over 4 factorial x minus 1 to the fourth plus, and so on with the stuff we haven't calculated yet. Double checking with the previous section, because we did this one as well, it looked like this at the end of the calculation from that previous video. A0 plus A1, x minus 1, A0 plus A1 over 2, x minus 1 squared, A0 plus 3A1 over 3 factorial, x minus 1 cubed, and so on. Plugging in A0 and A1, A0 is 2, A1 is 3. So every place I see an A0, I'm plugging in a 2 and 3 for A1. But then I can see these two certainly match up. This is now 5 over 2. Yep, that's what that one is. This is 2 plus 9 over 3 factorial. Yep, 11 over 3 factorial. This is 8 plus 6 times 3 is 18. So what's that, 26 over 4 factorial? Yeah, right, and it continues to be the same. Again, same answer, different solution. I didn't have the initial conditions in the previous video. Now, knowing initial conditions, I have a way of just calculating those coefficients without having to do all the algebra of the power series stuff that we did before.